Okay, thank you everybody for coming to today's session to recognize and hear from this year's winners of the Glushko Dissertation Prize. The Glushko Dissertation Prizes are supported by the Robert J. Glushko and Pamela Samuelson Foundation and are intended to recognize the outstanding dissertations produced in the field broadly understood of cognitive science, recognizing those individuals who've produced graduate work that crosses boundaries, creates new opportunities, and synthesizes in ways that advance the field of cognitive science in very deep ways. Before recognizing this year's 5 winners, I wanted to make sure to, I suppose I should have said, thank the committee. I'm David Danks, I should have said that, who I have the distinct honor and pleasure of chairing the selection committee for the Glushko Prize. And am joined on that committee by 5 absolutely spectacular cognitive scientists who give up quite a bit of time during the months of January and February. This year we had 50 nominations, all of which are reviewed by at least 2, often 3 or 4 members of the committee. That means reading a lot of text and reading at the end of it usually on the order of 15 to 20 dissertations each. So yes, we really do read the dissertations that are submitted through nominations for this. The other members of the committee are Morgan Berentz from University of Toronto, Jessica Cantlin from Carnegie Mellon University, Charles Kemp from Melbourne, Jeff Lids from Maryland, and Jenny Safran from the University of Wisconsin. And I particularly want to acknowledge Jenny, who will be rotating off the committee this year. So this year we are delighted to recognize 5 winners of the Glushko Dissertation Prize, one of whom is not physically present, but the other 4 are here. They are Kelsey Allen for her dissertation, Learning to Act with Objects, Relations, and Physics.
So we're going to get a picture taken here.
Yep.
With a nice framed certificate and a check for $10,000.
Kelsey, why don't you just go stay there and we'll get a picture with everyone at the end. Carolyn Baer for her dissertation, Developing a Sense of Certainty.
Isn't that nice? Yeah. Already framed.
The third winner, these are of course in alphabetical order, not any priority. Judy Kim for her dissertation, Visual, and the quotes are in her title, Visual Knowledge in the Absence of Visual Experience. The next winner is Sebastian Muslik for his dissertation on the rational bounds of cognitive control. And the final recipient who is not able to join us today is Tim Sainberg for his dissertation, Temporal Organization in Vocal Communication, Sequential Structure, Perceptual Integration, and Neural Foundations. So I'd like to recognize him. Can we get a picture of the...
Can we get all 4 of us for the website?
Yes, we want to make sure to get a picture.
Yeah,
I'll-
okay, can we do this? All right.
Kelsey, I'll take it. In addition to the lovely framed certificates, and as Bob mentioned, a $10,000 award. The Glushko Prize also comes with the opportunity to deliver a talk to the Cognitive Science Society Conference. And so we're delighted that we will have talks actually from all 5 of the recipients. Tim's talk will be a recording that will be played as the last one. So we'll begin with Kelsey Allen, who is now currently at DeepMind. Kelsey.
All right, there we go. Hi, everyone. Thank you so much for having me today. I'm going to talk to you about my thesis work on learning to act with objects, relations, and physics. So to start off, I just want you to imagine what you might have done this morning. Perhaps you woke up to the sound of an alarm clock, or ate breakfast with some utensils and perhaps a bowl, or made your way here by train or public transportation. But whatever you did this morning, I'm willing to bet that it involved tools and other human-made objects of various kinds. And you're not alone in using tools to get stuff done. As far as we know, tool use and tool creation are common across almost all human cultures, and these behaviors are one of the defining aspects of human intelligence. Our ability to use tools is also incredibly flexible and shows up in even our youngest children, who can do really incredible things like determine how to repurpose a shovel for a very unusual purpose of trying to get this super important out-of-reach Easter egg. And he's very flexible, right? It requires a lot of physical knowledge, and he uses a very rich trial and error learning process to try to be successful here. Now, unfortunately, as you'll see in just a moment, he's scooped by a child with an unfair height advantage, so he's not successful today. But hopefully his creative prowess will pay off elsewhere. And of course, over lifetimes, and importantly across generations, we can also learn to become incredibly expert tool users, like surgeons who can even do things like create artificial lungs to let us breathe. So what exactly is supporting these very complex natural behaviors in people? And could we reverse engineer some of these capabilities in machines? Now, to answer this question, in my PhD, I built new tasks to try to study human behavior that capture various aspects of physical problem solving. And then I spent a long time trying to reverse engineer these capabilities by relying on structured knowledge representations that cognitive scientists have long suggested are important for everyday human cognition. For example, we believe the world is composed of objects, and we know that even very young infants understand what these are. We know that these objects exist in relation to one another in the world, and that such relations govern the ways in which we map different scenes into shared representations that promote generalization and transfer. And finally, we know that these objects exist and move through space and time by obeying the laws of physics. And this guides both children and adults' inferences about everyday phenomena. My experiments in my thesis then cover multiple timescales of learning, from how people rapidly figure out how to solve a single physical problem through repeated failures, to how they build abstract representations, for example, like the notion of a catapult, to learn across problem instances, to how they even generalize different real-world embodied experience across lifetimes into different virtual worlds, which I'll look at using studies of children and adults born with one or even no hands. All of these projects are going to use the same cognitive task, which we call the virtual tools game, and I'm showing you here. The virtual tools game is this extensible 2D physics game where there's always a goal, which is always to get a red object into a green area. And what you can do is select one of 3 tool objects from the right-hand side of the screen and place it anywhere on the left-hand side. As soon as you place it, physics is turned on, and you get to see what happens. Now, the catch is that you only get to use one tool to try to be successful. And if you're unsuccessful, you have to reset the world and try again. So we made a bunch of different levels to test a variety of physical concepts in how people do this very rich general physical problem solving. And these involve things like creative thinking about how to move something you can't hit directly, like that catapulting example I just showed you, to others like supporting a table with a table leg such that a ball could roll across the top and into a goal. Or even things like levering open a box to allow a ball that's rolling down a ramp to enter it. And perhaps what's coolest about this game is actually just that people do a very wide variety of interesting kinds of behaviors here. And I just want to give you two examples of that. So on the left, this person is playing this table level, and they do a classic thing that people do, which is just take the largest object you can and try to hit the ball with it. And then they do an even more classic thing, which is to try almost exactly the same failed action again. But then they wait a little bit longer and sort of have this idea that you could place something beneath the platform to support the table. And they simply have to fine-tune that strategy a little bit in order to get the table at the right height so the ball can roll into the goal. On the right-hand side, this person is playing what we sometimes refer to as our PhD level, because it takes a long time, but eventually it's pretty satisfying. It would be very easy if only this silly black block wasn't preventing the ability to hit this ball. But they do kind of get the ball rolling, and while they might be optimistic that's going to work, and unfortunately it doesn't. So they revert back to a nice strategy of just get a large object to hit the ball, and then end up having to sort of use this weird hook thing. The hook thing doesn't end up working, but a sort of interesting thing happens when they have it collide with the black platform, which is that it can rotate around it to hit the ball with enough momentum to get the ball into the goal, and therefore are very satisfied and can move on with their life. So to understand the cognitive ingredients of this kind of very rapid trial and error learning, we built a computational model to try to reverse engineer this behavior. We call this model Sample Simulate Update, or SUP, in that it samples structured object-oriented actions to interact with the scene. It checks those samples by using a noisy internal physical simulation engine, and it updates its beliefs about good actions to take, called its policy, based on these noisy simulations as well as failures it makes in the real world. And these three components allow SUP to quickly converge on good actions based on just a handful of mental simulations and failed attempts. So the real question, of course, is does this model actually capture human behavior? And if you've been at CogSci, you've probably seen a lot of plots kind of like this, where we have a model on the x-axis and humans on the y-axis. And indeed, we get a nice correlation here across our levels. If we look at either the number of attempts people take until they find a solution, which is on the left-hand side of my screen, or if we just look at the proportion of humans or model runs that actually solve the level, which is shown on the right. But these are pretty coarse measures, and we have actually a lot more detailed data. So instead, let's look at what people actually specifically do. Now that's what I'm showing here. Visualized here are the first and last placements for both humans and our model across 4 representative levels. To interpret these plots, you can look at each colored point as an individual participant, with the color representing the tool they chose, pink, yellow, or blue, shown here on the right, and the position being where they placed that tool in the scene. And the model is shown as these sort of blobby background colors. Now, what's cool about this is that the model is capturing some of the very detailed behavior that we're seeing in people, right? The actual actions that are being taken. So for example, if you look at catapult, people are trying 2 kinds of initial strategies for the most part. They're either trying to hit the ball with the pink triangle, or they're trying to catapult the ball into the goal, mostly using the yellow block. And the model finds those 2 strategies the majority of the time also. That's what it tries initially. And by the last placement, both people and the model have converged on the correct action, which is actually to catapult the ball into the goal. But I also want to show you this fun failure case of falling A on the other side of the screen here. So falling A is actually a surprisingly easy level to solve. You can put any tool beneath the container, and as soon as you place it, the container will start falling and become destabilized, allowing the ball to roll out onto the floor. But people are super biased to try to put something above the container, which is much harder to be successful, and therefore they take a much longer time to find a solution. And this suggests that people are using, at the very least, more interesting contextual priors in order to play this game than what we've accounted for so far. If we ablate any aspect of this model, or replace components with different kinds of learning mechanisms, either learning simulator parameters or learning the prior using these fancy deep reinforcement learning techniques. They correlate much worse with human accuracies across our level, which also holds for a set of 10 cross-validated levels that we use that don't have any kind of hyperparameter tuning. So overall, we think that this supports our scientific claim with this game, that the efficiency of physical problem solving requires not just these structured object-oriented action representations, but also mental simulation and ways of rapidly updating policies based on failures. But of course, that's not really the whole story, right? We very rarely start each new problem from scratch, and instead we almost always reuse existing experiences to solve new and similar problems. So my favorite example of catapulting again, you can show very simple principles of catapulting to children using just what you have available at home, for example, as a maybe fun quarantine game. But those same principles could actually be used to catapult someone into a lake, right? Or it could be used to hurl a flaming rock at your enemy's castle. So what's the form of the knowledge that actually enables this kind of very rich transfer and reuse? So to test that, in this next experiment, we assigned people to one of 3 conditions where they then play 10 related levels that share some physical concept. And importantly, these related levels are going to randomize the tools that people have access to, as well as the sizes and positions of objects in the scene, but keep the physical concept consistent. Testing for everyone is then going to contain 6 levels, 2 of which are going to be matching the training condition that a participant was in. And one of these matched conditions is going to test transfer, while the other is going to look at indistribution. So what I mean by that is, for example, in this catapulting case, you have to catapult from the other side, but now you also have to catapult this red ball into this other red ball so that it goes into the goal. Or in the case of transfer for this table level, instead of just supporting 1 plank, you actually have to support 2 planks simultaneously in order to be successful here. We find that people do get better throughout these training levels. They get better very rapidly. And in the testing conditions, they often perform better than people who are untrained, even in 2 out of the 3 transfer cases. And here, people who are trained are being shown in blue, people untrained are being shown in orange. So anywhere the blue looks a lot higher than the orange, we're seeing an effective training. And it doesn't happen in all levels, which you'll see, and there are very interesting reasons for that, but unfortunately, only 15 minutes for a thesis. I don't have enough time to talk about that. But if you're interested, I'm happy to answer questions about it. So now, of course, the question is, what exactly are people learning, since we can see that they are learning and generalizing some of that knowledge? Let's propose we're going to use exactly the same SUP model for how people learn within a level, but now we're going to suggest that across levels, they learn these relational strategies that are supposed to be something like giving us a notion of catapult. And how should these relational strategies be represented? So as I've mentioned, they need to be generalizable, right? They have to apply to arbitrary objects based on that object's role in the scene and in the physics. And so we represent those relational strategies using a probabilistic grammar that can support these abstract representations by using symbols and rules and manipulating those across relations between objects as well as object properties themselves. We're then going to learn a relational strategy with techniques from classic relational reinforcement learning, and that's going to give us rules that are comprised of this grammar that can explain prior successes. And I'll give you an example of that on the next slide. So what exactly is this model learning? Let's take, for instance, a model trained on the same catapult levels that people saw. It then learns this strategy, which is a program that's going to be relatively inscrutable, but let me translate it to English. All this means is that I should pick out a wide object in my scene. I should find a location away from the middle and above that object. And I should place, in this case, a tall tool here, which is substituting for something like the mass of the tool. When we use this model as the prior for the catapult transfer level, we find it does pretty reasonable things, like putting the large block high above the catapult lever, just like people do, which is, nice and relatively reassuring. And in fact, across all of our different transfer levels, the model finds training to be helpful for precisely the same test levels that people do. And it finds training isn't helpful for the same levels that people don't find training helpful for as well. So this suggests that people learn across problems by mapping those problems into these relational symbolic representations, as has been suggested by literally decades of analogy work. And these can then guide more efficient search with a noisy physical simulator. But that's not even the whole story, right? So everything I've talked to you about so far has been in these virtual worlds on short timescales. But of course, most of our actual experience happens in the real world, not in these physics games. And so in this last project, we had the really unique opportunity to look at how people's real-world embodied experience over their lifetimes might impact the kinds of very general cognitive strategies they use to solve physical problems. And to look at that, we studied both children and adults who grew up with 2 hands, but also critically people who were born with limb differences. That is, they had 1 hand or even no hands from birth. And now normally comparing these populations for something like physical problem solving is pretty difficult because the capabilities of these individuals is simply distinct. In the physical world, they can just do different things. But by studying what they do in this virtual environment, we can actually equalize the action space between people born with different bodies, since everyone can control a cursor pretty effectively, as we checked in a motor pretest. Now, one of the most interesting findings here is that actually there's a lot in common. People born with limb differences are about equally good at this task, achieving approximately the same accuracy across the problems as 2-handed individuals. But the dynamics of how they arrive at solutions differs. So in particular, people born with limb differences, but especially adults, seem to take fewer attempts in the game to arrive at solutions relative to people born with 2 hands. But the amount of time that they spend thinking before each attempt is significantly higher than for people born with 2 hands. And this can't be explained by their ability to use a mouse. In fact, people with limb differences are actually slightly faster in cursor control tasks. Overall, we think this suggests instead that individuals born with a limb difference actually learn to make a different trade-off between thinking and acting, thinking more and acting less. And while there's still a lot to learn about how far these kinds of learned abstract cognitive strategies generalize, we're pretty excited about this initial step, suggesting that they extend to problems even when the capabilities for action are made equal. So to wrap up then, today I've shown you how people learn to solve physical problems across many timescales, from learning across just a few actions within a single problem, to learning abstractions across problems, and then even to learning these abstract cognitive strategies for physical reasoning across years of embodied experience. And to reverse engineer this behavior, we needed computational models built upon objects, relations, and physics. In the work I'm doing now at DeepMind, we're trying to extend these ideas past how people use objects to solve problems, towards how they might design new objects to solve new kinds of problems. Like in these cases, changing the flows of fluids to move through space. Again, relying on these same principles of objects, relations, and physics. And with that, I'd like to quickly thank my advisor, Josh Tenenbaum, and my close postdoc mentor for my PhD, Kevin Smith, for helping me build this toolkit. And if you'd like to find out more, please check out any of the references here or check out my website, and I'm happy to take any questions we have time for.
Any questions come in online, I'll read them, but if anyone has questions, please feel free to come to the mic. Either one.
Okay.
Wow. The last work you described used the timing as a basis for inference, and one has to wonder if it would give you any further insights into mental simulation to have included time, the time to response into your modeling as opposed to just accuracy.
Yeah. So in the initial looks that we had at this game, We didn't see any particularly interesting timing profiles, but we did actually look at that a little bit in our initial paper. So I think it could be very interesting to look further at that and try to correlate that with the model, how much the model spends actually time thinking before acting. But we haven't seen any sort of interesting behavior in normal adults on that front in the main version of the game. Thanks for the question.